All right, so this is for worksheet 14.3. Okay, so basically, looking at doing some types of derivatives. Now, the first part of my notes I'm going to skip. I will let you look at those. It is more for just reviewing from Calc 1. But just a quick summary of here. So if you're doing the derivative of this function here, and say you get tangent line, and say this is f of x, this would be f prime of x. And the way we found that by limit derivative, so like f prime of x would be the limit as h goes to 0 of f of x plus h minus f of x over h. Or as an example here, let's say this function is, say, x squared. Therefore, the derivative of this, f prime of x. Now, keep in mind, there's also, that was Euler's notation. There's df dx equals 2x. So there's two types of notation there. And then if we do a numerical derivative, let's say at 3, df dx at x equals, let's say, 3, or f prime of 3 is 6. All right, so quick review of the notation piece is what I was getting at there. Okay, so now let's go to three-dimensional here. Okay, so what is a derivative three-dimensional going to look like? Well, first off, let's look at a sheet here. And by a sheet is a part of a three-dimensional graph. So let's say this is this part of some three-dimensional piece, like on a hillside or something like that. So let me draw in my axis. Okay, so here's my z-axis, my x, my y, and let's say we're looking at doing a derivative at some point right here. So basically what you're trying to do here is you're looking at taking, like I say, a slice of bread out of this. So I take a knife and slice it. So basically what it'll look like would be, let's just take this straight down here. And visualize a slice of bread. Okay, so we have is something like that. Okay, so basically what we're doing here is we're doing what we call partial derivatives. So one, I could do it in terms of, say, x in terms of z, or two, I can do y in terms of z. And this is kind of like this last one I did in terms of y. So then if I go back and do it in terms of x, let's see here, let's do green. Okay, so again, visualize taking another slice of bread. So therefore, that would be in terms of x. So what's our notation for partial derivatives? Well, it is, now notice up above it was a printed D. A partial derivative is a cursive D, df dx. Now that's Leibniz notation. Euler's notation would be f, and you put an x on the bottom of x, y. And that would be a partial derivative of x. So if I did a partial derivative of y, the notation would be partial derivative df dy, or a partial derivative of y of x, y. Okay. All right, so let's go through an example here. So if I had, let's say something like this, say z, or also can be written as f of x, y, and I would have, let's say, x squared y to the fourth plus 3y squared plus 4x. Okay. So let's do in terms a partial derivative of x. So the notation would be partial derivative of f dx, which would be Euler's notation, f derivative x xy. So basically what you're doing here is you're going to go through and you're just looking at the x values only, and you're just going to do the derivative of those. How about the other things? Those are just constants, and they just come along for the right. So what's going to happen to the 3y squared? Well, the derivative of that is this zeros, because it's just a constant. So what we would have here would be 2x y to the fourth plus 0 plus 4. And clean that up, would be 2x y to the fourth plus 4. So let's say if I want to do the derivative of, and again here, partial derivative of y, what would that look like? Okay, so this would be partial derivative of f dy, or fy xy. And therefore now we're just looking at the y values. Anything else is just a constant and comes along for the right. So what we have here is x squared, so we have 4y cubed plus 6y plus 0. Or in this case, you would have, clean this up, 4x squared y cubed plus 6y. Okay. Now, there's some more examples in my notes so you can kind of see a pattern. So I suggest looking at those other 2 or 3 examples I have. I'm going to jump to a higher order. What happens if you do like a second derivative? What the notation would look like for that. All right. So let's say we have f of x, y, and I'm going to do the partial derivative d dx. Okay, so that would give me my 2 notations, f x xy, and that would be partial df dx. So what would it be if I did another partial derivative d dx of yeah. Well, what keeps track of the derivatives is right here. So, since I'm doing another derivative of this, it would just be f of x xy, like so. Or square df dx, like so. So what happens if I did partial derivative of x and then did partial derivative of y? So let's say dy of xy xy. Now here's where I don't like using Leibniz's notation. I just stick with Euler's. And therefore my notation would be f of xy of xy. Okay. Now the question is going to happen, what happens if I do it the other way, first y and the next? Well, that would be f of yx of xy, and those would be equal. So order of the derivatives does not matter. Okay, the order doesn't matter. All right, so let me go through an example so you can see how that might look. Okay, so let's use this one here. So f of x comma y, and let's say you have 3x squared plus y squared e to the x. So let's do the derivative of x first. So again, if you're looking here, we're just doing derivative of this and this only. Everything else is just a constant and comes along for the right. So this piece here would be just 6x and y squared e to the x. All right, so now let's do the derivative of y. So f x y Okay, so the only thing we're doing derivative now is this. This is a constant, so I have 0 plus 2y e to the x, or 2y e to the x. So let's go the other direction. So let's say I want to do the derivative of y first. Okay. So coming back here, that would mean I just do in this piece here, this part here would be 0. That would be as a constant. So it would be 0 plus 2y e to the x. Now do f of yx. So now I'm going to do just the derivative of this piece. So that'd be 2y e to the x. And notice you get the same thing either way. Okay, so order doesn't matter. All right, so the last thing I want to do is come back and show you a little bit of implicit derivatives, a little shortcut maybe, now that you know what partial derivatives are. So let's come back and let's use this one as an example. So 3x to the fourth y plus 5x plus 4 equals 6y. So from Calc 1, remember you only had to worry about like y primes on here and here, but you still did the derivatives of x's. Okay, so you had to do the derivative starting with this here. So derivative of x, you have 12x cubed y plus, now it'd be 3x to the fourth 1, but you have y prime. Okay. Now, next one be 5 plus 0 equals 6, but then you have y prime. So what you have to do is put those two on the same side and factor out the y prime. So let's move things around. And remember, when you move things around from the equal sign, sign changes. So a negative is going to occur here somewhere, depends on where you move things. So you have 3x to the fourth y prime minus 6y prime equals 12x cubed y minus 5. Okay. So now factor out the y prime. I have 3x to the fourth minus 6 equals 12x cubed y minus 5. So therefore, y prime, or dy dx, would be 12x cubed y minus 5 over 3x to the fourth minus 6. All right, so a couple things. Now also too, if I multiply by a negative, all the sign changes and all that, okay? So remember, this would be the same thing as negative 12x cubed y plus 5 over negative 3x to the fourth plus 6. Okay, now let's do the same thing, but by by partial derivatives. All right, so let me rewrite this, and we'll come back and look at this answer here in a second. So I have, again, 3x to the fourth y plus 5x plus 4 equals 6y. Okay. So first off, let's go ahead and let's do a partial derivative of x. Okay. Now I would have to set, move this thing over here. So let's write this as a, let's say 3x to the fourth y plus 5x plus 4 minus 6y, and therefore this would be my f of x comma y. Okay. All right, so let's do it in terms of partial derivative of f dx. Okay, so that would mean I just worry about doing derivative of these. Everything else would be 0. So that would be 12x cubed y plus 5. Now let's do the partial derivative, df dy. Okay, so let's do green on that one. So now I'll just concentrate on my y values. So I would have 3x to the fourth. Yeah, this would be 0 and minus 6. Okay. All right, so now doing a division here. So if I do df dx divided by df dy, okay, that means I had df dx times dy df. Therefore, df's cancel, and that would give me dy dx. So if I divide my partial derivative of y, which would be 3x to the fourth minus 6, over 12x cubed y plus 5. Oops, what did I do here? Whoops, I got them backwards in it. Yep, I need to start with this, right? I got it backwards. So 12 x cubed y plus 5, there we go, over 3x to the fourth minus 6. Okay, but now notice we are off by, should be a negative here, right? You can't quite see it there. And the reason is because you got to move, remember partial derivatives, you move everything to one side. So one thing you got to remember is by moving over, you subtract things. So there should be a negative with this to change your signs. That's the only thing I remember of this little trick. So anyway, there's an example of doing partial derivatives, but do it implicitly. A little bit faster, I think, once you get used to it. But I say you have to do retrain your thinking. And the one thing is you have to remember about your negative there. Okay. Other than that, that's it. So that's your first introduction to partial derivatives. We're going to be doing a lot more of these. So wrap your head around it. There's more good things to